Here I'm going to show you a cascade of functions using Desmos, DESMOS.com. This is an online utility that helps you graph things really quickly and really nicely. What we want to do here is just take a look at functions and their graphs, not in a very detailed sense where you will have to produce from scratch a whole bunch of nasty looking graphs, but in the sense of predictability of effects on the graph based on changes to the function. So what pieces of the function dictate what behaviors on the graph and so on. So first of all, I'll just start with everybody's favorite y equals x, and everybody knows what that looks like, the perfect diagonal straight line. That's not very interesting. So let's say I upgrade that to x squared. Okay, do you know what happens? Well, we get a parabola. The vertex of the parabola is at the origin. Everything is positive on the graph because no matter what we plug in for x, whether it's negative or positive, the output will be a positive number because we're squaring it, right? What if I was to come up here and insert so I haven't changed it yet, I'm getting ready for grouping. What if I put a -1 on the inside of the parentheses? You probably played with things called transformations of graphs in an algebra class at some point, and you learn how the insertion of constants by addition or subtraction can shift a graph left or right or up or down. If we insert a constant inside the function in the way I'm doing here, this is going to shift the graph to the left or to the right. Now this is sort of counterintuitive because I went from x to x -1, so I inserted a -1, but it shifted the graph to the right in the positive direction. You may think that's backwards, but think about it. In the original graph x squared, to find the vertex, we had to look at where 0 squared sat, right? And so here, when we put in a -1, well, that same vertex will be found when 0 is being squared. Well, where would 0 be squared on this new function? Well, it would be found when x is 1. If we plug in x equals 1, we will get 0 squared. And ta-da, there's the vertex. Now, what happens if we go and put a constant on the outside of this? I'm going to add, and this time I'll just add another 1. Well, that shifts it up because whatever y values we got out of this function, all this does is add 1 to each of them, and so everything moves up by 1. Now, we just talked about rational functions a short while ago, so let's get really nasty here and add a denominator. And my first denominator is just going to be x. This is going to destroy the parabola. What we're going to see is not a parabola anymore, but let's think about the impact of putting a division by x on this function. First of all, we'll create a situation where we're not allowed to plug in x equals 0. So the graph will not have a point plotted on the y-axis where x is 0. Further, in the original version of this, everything was positive, right? Numbers were being squared, we were adding 1 to them. When we divide by x, then when x is negative, the overall value will be negative, and when x is positive, the overall value will be positive. And so when I divide by x, we're going to see this function snap apart at x equals 0, and we will also see part being positive and part being negative. Ooh, well, that's only a positive part. Does that mean I was wrong? Well, no, that just means that I don't have my window opened wide enough. And there we go. So now we've got more of the details of the graph. Just the scaling of the axis is a little bit wacky. We could fix this, right? Well, it's pretty much square. The window you're seeing is not square because of what I've carved out for the view. But you see the graph snap apart at x equals 0 because we can't plot a point there. There's other behaviors as we get closer to x equals 0 that is called asymptotic behavior. You can sort of see here that if we zoom way out, the part of the graph here just looks kind of like a straight line, right? And the farther out we zoom, the more intense that gets. That's called asymptotic behavior because the function looks an awful lot like a straight line, even though it isn't. If we go back here and divide by x squared instead, think about what's going to happen. The graph will still be broken at x equals 0, but now everything will return to being positive again. And so this is where the fun of rational functions comes into play. You can create all sorts of interesting behavior. You can break the curve of the function at places where the denominator is 0. And you can have regions where everything is positive, where everything is negative, and so on. What happens if I go up here, and I'm going to make this -1 instead, okay? Something new was introduced there, and that was this point. What I did was I just created a numerator that can give the value 0. So there's a value for x that if I plug it into the numerator, the entire value of that messy function will collapse to 0. In fact, it's 2, right? When x is 2, the numerator will become 1 squared minus 1, which is 0. Okay? And so we've introduced a root of this function, a 0 of this function. So there's all sorts of markers and behaviors of graphs to look for. It'll leave you with one last thing here. Let's say I really want to destroy this function, so it's not only broken at the origin, now I want to break it at x equals 3. Haha, there we go. And now I'm going to zoom in a little bit more just because there's interesting stuff going on there. So I've broken the graph at x equals 0 and x equals 3. This vertical red line is not actually part of the graph. That's just the plotting algorithm in this website, jumping from a point way, way down below to a point way, way up high. It's not actually part of the curve. But there's a break, a vertical asymptote in the graph there. There's another break over here at x equals 3. You've got places where the function becomes 0. You have behavior that's called decreasing, which probably doesn't need a whole lot of explanation. The graph is decreasing from left to right, right here. Actually, it's decreasing here as well, and it's decreasing here. Wow, this is a function that decreases everywhere. That's pretty exciting. You can imagine what increasing might look like. But this is what you want to be able to do, is take a look at a function and imagine what graphical features it might have based on where the denominator goes to 0, where the numerator goes to 0, and any other kind of patterns or interesting things you might note about it.